Okay, so it's my pleasure to welcome Umut Acar from Carnegie Mellon University. So Umut got his PhD also from CMU with Guy Blalock, and where he did really fundamental work on self-adjusting computation. This kind of work is getting more traction now, and he's done very interesting work in parallel computing, theory of parallel computing, lower bounds, and things like this. And this is a direction now that they've been working on for quite some time. So go ahead.
Okay. Thank you. Thanks, Martin, and thank you everyone for coming. So I would like to talk about this. It's, by the way, great that I'm continuing on Vivek's thread here. So I'm going to take advantage of his introduction and skip some of the material. But if you have any questions, please ask. So I worked on parallel computing early in my career, and then I took a break and worked on some other problems. And then recently I returned to this problem again about 3 years ago. So this is an overview of the work that we've been doing for the past 3 years with a group of people at Carnegie Mellon and at CMU, at Carnegie Mellon and at India. So I'll try to give a conceptual overview rather than getting into the technical details. But again, just ask me if you have any questions. So as Vivek told you, parallelism is here. We all have parallel computers nowadays that have the power that's essentially equivalent to what we used to have in a supercomputing about 50 years ago. Okay, well, much more powerful probably. So hardware is here, but parallel software continues to be a challenge. Right? The challenge is, how do we design, analyze, and implement, also proof correct parallel software? Now, in this workshop, there has been a lot of research and a lot of reports on how to prove correct parallel software. Now, that's of course, that assumes that parallel software is written in a particular way. If you write parallel software in a different way, you don't have many of those problems. And that's actually the thread that I will be exploring here. So specifically what we need in order to solve this research challenge is broadly applicable models, as in the RAM model, for example, that we all use in order to solve design serial algorithms, implement serial algorithms. Programming languages and systems where we can actually write parallel code, and of course, algorithms and implementation. Now, on the flip side of the coin, we have important educational challenges. Right? So people write parallel code today, and they write, as Vivek said, right, they start with a serial program, and they tweak the code and hope that that would work. Okay, so that's just, it turns out that's not really the way to go. So we need a new way. So what should that be? We don't have an answer, but it's an important challenge. So anyway, we've been working on this. So in this talk, I'm going to give you an overview of what we've been doing, try to address these challenges. So our starting point is, again, as Vivek said, is structured parallelism, or implicit, sometimes it's called implicit parallelism, managed parallelism. That's been shown to work quite well, right, over the past 20, 30 years. So it's been implemented in Silk, C++, in Java, for example, as Habanero, also in fork-join Java library, in Extend. In the functional world, it's been implemented in Parallel Haskell, Parallel ML.
These can be understood.
Sorry,
the language. Is it a joke or the?
Oh,
you cannot understand any of these languages.
Good point. Yeah. So I operated my Mac, and my spell checker doesn't work anymore. So I'm sorry. You know, iSpell doesn't work. So it's one of those problems. Anyway, so the point here, what is the essence of structured programming? What it is that it's really programmer specifies, and the language, the programming language, manages parallelism. So if you're not familiar with parallelism, you can think of it as the GC for parallelism, right? Just like in garbage-collected languages, you don't worry about how the memory is actually managed. You know, you don't even know when you allocate often. It is done for you. The garbage is collected for you. So managed parallelism can be viewed a lot like that. So the programmer simply specifies where the parallelism might be, and the language takes advantage of it. So specific instances of this typically, I'll be focusing on two versions here, fork join and async finish, which is what Vivek talked about, for example, focused on. And also, you can add parallel for into the syntax, which is just basically a syntactic sugar. It can be implemented in terms of fork join and async finish paradigm. Basically, the programmer indicates parallelism using these keywords. Now, a very important point here is that the programmer can read the code that he writes by aligning the syntax, effectively covering these keywords up, and what he sees is a serial piece of code that he can reason about. So that we say, that we call that property sequential semantics. So the code actually has sequential semantics. Now, of course, parallelism is all about efficiency, right? If you don't get efficiency, well, you might as well just go write serial code, make your life easy. You know, what are you doing? So cost semantics allows the programmer to reason about the efficiency of the code that's written. Okay, so specifically, in both of these models, fork join, async finish, all you need to do is analyze work, that is the total amount of work that the computation does, and the span, that is the longest sequence of dependencies or chain of dependencies in your computation. And these two measures can be used to estimate the efficiency. Okay, those two suffice. Now, of course, the challenge here is, given this nice, very high level tools, so to say, programming language tools, how do you design the actual language and the runtime system and compiler to match the provided semantics? So a very simple example, right? Suppose that you have, you want to write Fibonacci in the dumbest possible way. You would use the recursive definition of Fibonacci. And you can say, well, look, I can execute these two pieces of code in parallel. So you put a fork in front of that call. And then this join here indicates that you have to wait for these to finish before you continue, because you're going to sum the results up. So the same can be expressed in this way. You have a finish block. And inside the finish block, you can execute these two calls in parallel. So those are essentially identical syntax. There's a difference, because this finish block can have dynamically many dependencies, whereas the fork and join, you know statically you've got a constant number of dependencies coming into that join. Okay? And parallel for, often supplied by many languages, it's very convenient to express a for loop with lots of parallelism. Any questions? Suppose that you have, you want to compute the maximum of a maximum value in an array. You might start with this code here, which is what you're all used to, right? So you have a for loop that iterates over the array and finds the maximum by keeping track of the current maximum. Suppose you want to do this in parallel, right? So we've already seen parallel for. What I can do is I can just replace that for with parallel for, and I'm done, right? So very simple. Does everybody buy that? No? So what would go wrong, right? You're all experts on this. What would go wrong is that if you do this, well, you actually have a race condition, because that max will be banged by many parallel threads at the same time, so this won't be correct. Okay. So any ideas? How might we write parallel for to be correct? Parallel reduction, right? So that's exactly what Thomas says. You have a divide and conquer algorithm that says, if I hit the base case, return the number in there. Otherwise, you fork two recursive subcalls and then wait for them to finish, and then calculate the max as the max of the two calls. Very simple. So incidentally, this piece of code that you wrote is actually purely functional. Okay? It's correct, and but it's also purely functional. That's nice. So an important point is that purely functional code is parallel safe, because you just can't have data races, period. Okay? And to understand this code, we just basically allied fork and join, and then we have a regular serial code. Now, we can analyze the work in span. To analyze the work, we simply analyze the amount of work that this call does. We can prove that it's linear because it goes through each element one by one. And then span is the longest chain of dependencies. We can prove that it's logarithmic because it divides the array in the middle every time it recurses, so this span is logarithmic. So that means that there's plenty of parallelism here. Very few dependencies, a ton of work to do, so plenty of parallelism. And then we leave it to the language to manage the parallelism, right? The language decides how it actually runs the parallel computations, okay? So very nice, very high level kind of programming model. So how does the language actually do the business of mapping this to hardware? So what it does is it creates a DAG of threads. Sometimes these are called strands, sometimes they're called tasks. There are many, many words to these things, but I'm just going to use for simplicity the term thread. And each thread corresponds to basically a basic block, okay, more or less. But more generally, it corresponds to a serial piece of computation that's not interrupted with these forks and joins. So this red part corresponds to that, green part corresponds to that, and so on. So what you get is a DAG of threads. Okay, any questions? Good. So then what you do is you take one of these things, and you've got, let's say, 4 cores. You simply map the DAG to the machine that you have by using a scheduling algorithm. The scheduling algorithm simply goes and basically traverses this DAG, mapping each thread to a processor, making sure that the dependencies are observed. For example, you might execute A first, and then executing A opens the way for B and C to be executed. You can execute B and C. Now you can execute D, E, F, G. So if you've got 2 processors, for example, you might choose to execute D and F, and then F and G, and so on, right? So you continue in this way. Simple, so that can be written in this way. So now the work here is 22, the time 2, which is the time it took to run this computation on 2 processors, is 12, the number of steps here. And here's the schedule, right? So there are many schedules I can have. This is a breadth-first schedule. Here's a depth-first search schedule. So that executes in a slightly different way, still observing the dependencies. That's important. What if I have infinite number of processors? Is that even realistic? Mathematically speaking, nice. Huh? What if you have infinite number of processors? You know, I can also do that, and I can imagine executing this on an infinite number of processors. I don't need, in this particular example, more than 8. I can do level by level, and that gives me 7 steps, and that is the notion of span. Okay? Span corresponds to executing this on infinite number of processors. Okay, so work in span, basically 2 ends of the extreme, on 1 processor and on an infinite number of processors. Conceptually, it's actually quite easy to analyze. So now a very important theorem is that it's called Worktime Principle, also proven by Brandt, actually a mathematician in 1974. Now, given the work and the span of a computation, the time on P processors is W over P plus S. Okay, very important theorem, W over P plus S. Can I do better than W over P? I have W work, I have P processors, I can only execute P things at a time. I can't do better than W over P. Can I do better than S? Remember, S has to follow the dependencies. S is the time that you need for infinite processors. You can't. This theorem says you can do W over P plus S within a factor 2 of optimal. Very good. Except it does not account for the cost of scheduling and the impact of scheduling on things like locality, on memory management, etc. That's a very high-level theorem that does not take into account any of the costs that we actually care about. Okay? So, right, you can prove, like you can make some definitions, right? We typically say an algorithm is work efficient. Its work is equal to theta of TS, TS being the serial work. We say that it has a large amount of parallelism. If W over S, work spread over span, is a lot greater than P. And then we talk about speed up, which is the time that the serial processor, serial execution takes divided by the time on a P processor. And that is the speed up that we hope to maximize on parallel processing. Now, a theorem is that if you've got a work efficient algorithm, and if the algorithm has good speed up, then you can expect linear speed up. That means as you increase the number of cores or processors, you should be able to see a corresponding decrease in runtime. Okay? So this is all theory. Let's see how it works. So we coded up that parallel max, right, in a high-performance C library. This is how the speed, this is the time over 16 cores or 16 processors. So it's sort of decreasing quite well. You know, it looks so good. Now, if you look at the speed up, this is the speed up that you see. Less than 1. It's actually slower than the serial piece of code. So that's the practice. And this is the gap that we need to solve in order to make parallel software a reality. So how do we do this? Well, so what's the gap? The gap really comes from the fact that the theory does not account for some very important costs, such as cost of creating threads, cost of scheduling, and cost of the disruptions to the management of memory, to locality. Okay? These costs are extremely substantial. 1 to 2 orders of magnitude are typical. They can be eliminated by very careful performance debugging, but that's just not science. Okay? We want to simply, in the context of a managed language, we want to do this automatically without having to go through this labor-intensive, expansive performance debugging. Now, even if you can't do that, what you get is often non-portable code because you specialize to a particular hardware. So you might engineer your code for a particular hardware. If you take your binary to somewhere else, it just doesn't work. So how do we close this gap? Well, it's really good old PL research. Okay, so what we want to do is be able to extract high performance from high-level code. Okay, we don't want to have high performance code at all costs. We want high level code and high performance in the same place, right? So how do we do that? We have to extend the theory to account for practical costs, and we have to realize that in practice, okay? So, right, so it's very important, if you want to achieve both of these things, high level code, high performance, that I believe we have to work on both functional and procedural languages, because expressiveness you get from a functional language, performance you get from a procedural language. There's a gap here. In order to close that gap, we have to work in both directions. I don't see any other way of actually solving this problem otherwise. So indeed, this is what we've been doing. We've been developing techniques for C++ and also ML, a strict functional language, and trying to close this gap. So in the rest of this talk, I'm going to give you an overview of these 2 projects and then tell you how we use them in education, okay? Good, so first part. So over the past 3 years, we've been building a C++ library. This is very lightweight syntax, made possible by lambdas that were introduced in 2011, well, more later, but in C++ 11. This library we call a Passel. It's our primary goal here is to understand performance, but it's designed for research and teaching. So it uses an innovative work stealing scheduler that's simple and adaptable. If you want to, for example, do some research, it's very easy to work with. It's polished. It can be done. There are lots of tools in this library that aids in experimentation, so you can take measurements, understand where things are going wrong, etc. Most importantly, which is what I'm going to talk about here as far as this library is concerned, it supports automatic granularity control. We'll just see what that means and how it helps. We've looked at many example applications, a whole slew of benchmarks. Most notably, we actually were able to come up with the first work-efficient parallel unordered depth-first search algorithm using this library. So in the rest of this part, I'm just going to give you a brief overview of the granularity control technique that we use. So let's go back to see what I mean by this. Let's go back to our parallel max speed-up curve. So this was the curve that we got. We expected something like this, linear, right? Or linear up to a point and then perhaps sloping down. That's also natural due to hardware limitations, but this is what we get. So to understand the speed-up, we took some measurements. Okay, so what we did is we compared the sequential iterative code with the sequential divide and conquer code and with the parallel divide and conquer code executed on a single processor. And what we see is that the sequential divide and conquer code is 6 times slower than the sequential iterative one. And the parallel uniprocessor run of the divide and conquer code is about 15 times slower than the sequential one. Okay, so in total, we have approximately factor 90, almost 2 orders of magnitude overhead that we obtain due to parallelism. Now, there's nothing special here. This is completely typical. Probably anyone that does work in this kind of field will tell you. You go from a serial to a parallel algorithm, you have some overhead because, well, you have to change the algorithm. You go from a serial run to a parallel run, well, you have to create threads, manage them, you have some overhead. These two together basically account, even in this simple benchmark, 100-fold overhead, basically. Okay, any questions? Right. So how do we control this? Somehow the programmer needs to reduce this overhead. What's a good way to do that? Any ideas? Change the granularity, right? So very simple. So all you have to do really is, right, change your code max so that when the problem size is small, it simply reverts to the serial execution. Then you take care of both of the overheads at sort of the corners of at the leaves of the computation where things matter, and then all the rest can now be amortized. It turns out this technique can make many, but not all, parallel algorithms strongly work efficient, meaning that comparable to, using this technique, you can get comparable execution times with serial. Now, the question is, how do you choose this cutoff constant? You can guesstimate, you can say, okay, 10, 100, whatever you choose today on this particular machine is probably not going to work on some other machine. Okay? And it turns out it's actually a lot deeper than it seems. Sometimes it's possible to solve this problem. It's also context dependent. Sometimes it's possible to solve this problem in a particular context. But if you have a higher order language like ML, well, where functions are passed around as first class values, it becomes even more tricky to do this. Okay? So far, the approach to this has been simply performance engineering. Okay? You sit down and you figure out what these cutoff constants are, spend hours of time, and then optimize. Okay. So let's see actually first let's extend the theory very briefly to account for these things. What we can show is that this is not a hard theorem, but it takes some work. If tau is this overhead, parallelization overhead, it really factors into your Worktime principle as a multiplicative factor because you can't distribute it. It's the kind of overhead that cannot be distributed, so it becomes as a multiplicative factor in front of both the work and the span. Okay. So in order to understand how we might solve this problem, let's suppose that we have access to an oracle, okay, that predicts the runtime of a particular parallel thread. So what we can say is that at the point where we're going to create parallel tasks, we can say, well, hey, Oracle, is the branch that I'm going to execute, okay, left or right, are the two branches actually substantial enough to amortize the cost of parallelization? Okay, and that we can determine by some constant kappa. So if the two branches are bigger than kappa, go ahead and parallelize. If not, serialize. Okay, so a very simple idea. Basically, we say, if both of the branches are bigger than kappa, then we're going to execute in parallel. Otherwise, we're going to serialize these two calls and continue. That's basically what this algorithm does. With such an oracle, you can prove that the overhead, this 100-fold overhead, can be amortized to whatever degree that you like, essentially. Okay, this is under some assumptions, but yeah, I believe this is under some assumptions oh no, sorry, this is independent of assumptions. We can prove that this can be amortized completely. Now, how do we build such an oracle? Any ideas? Yeah, no, good point. You can try, okay? So one idea would be, instead of the oracle, so you can say, well, the programmer can give me some information, right? The programmer can give me exact times. Maybe it can indicate how large this is. Again, you go back to the same problem, okay? You're still dealing with constant factors and et cetera, so difficult to solve, okay? A very simple idea would be to say to the programmer, well, you just give me an abstract measure of the complexity, or the abstract measure of the time each computation is going to take, right? A very good metric to do that is simply to say, tell me the asymptotic cost of each of these threads, and then at runtime, you can determine the actual constants hidden for that particular architecture, and then you have your oracle. Is that clear? So let me illustrate this with let me just summarize here. What we do is, for each parallel, basically a fork or thread, we ask the user to provide an asymptotic complexity function or work function, asymptotic complexity function abound on the work, and we complete from this the actual runtime by machine learning the constants that are specific for that computation on that particular machine, and then we have the oracle. Okay, so here is the code in C++ for array max. So let's go through this carefully. So we define first the granularity controller, the top line there. And then this is our code for array max. This piece of code here says, well, we're going to granularity control this statement. And the complexity is linear. Note that I just simply return the size of the array. And then this is the parallel section. And then I optionally provide a serial piece of code that simply executes when the input is small. And the compiler, well, the library decides when to execute the parallel, when they execute the serial, by machine learning the constants that are hidden in the abstract, in the asymptotic notation that's in there. Right. Yep.
Property, why do you need the programmer to provide the serial?
Very, very good. You don't. Yeah, you don't. So yeah, very good. So you can, very good question. So you don't need this as optional. You can simply elide. You can fall back to the serial execution. Before completeness, I provided that. So it's a very simple change to the system. So this is your speed up, right? That you were get before granularity control, and this is the speed up without granularity control, and this is the speed up with granularity control. So, any questions on that so far? Okay, so.
No.
What do you mean by this question?
Structure like that they happen before in certain shape, it's not just arbitrary program.
No, it does in the sense that I take advantage of the recursive nature of the calls. If they were not recursive, I won't be able to learn the constants.
Let me ask you a question. So do you need to do that for every parallel execution, or you do it once?
I don't profile, so this is at runtime.
So you do the work twice?
Every round does it. But it turns out the asymptotic complexity is such an easy to learn, it gives me such a good target, I can machine learn it very quickly.
But you make the assumption that reading a variable or writing a variable doesn't have any side effects.
Sure, I do make this assumption. Yes,
right,
yeah, so this worked on their model of side effect free, yeah.
And also you don't account for other things that run on the machine, right?
Oh, it accounts in the sense that it adapts.
It adapts, okay.
Yeah, but I can't say that we studied that carefully, so that's a good point, so we didn't study that carefully, yeah.
How sensitive is to mistakes in the asymptotic complexity, so if the user gives you a wrong?
Very good question. We don't have a proof of this, but it turns out to be not very sensitive. If it's approximately close, you're okay. And the reason is that you just need a lower bound.
Oh, okay.
Right? You just need one-sided precision. You just want to know, is this bigger than some certain threshold? So that seems to be a very coarse approximation. And in many cases, you've got enough parallelism that you can use the force non-parallelism, etc. So we probably have not proven this, but that appears to be the case.
But if you're, let's say you deal with an algorithm that has linear amortized complexity, but the user gives you n squared, would that make a big difference? So if the difference in the true complexity and the complexity that you get is 1 or 2 order of magnitude.
Yeah, n squared can make a difference. I don't have numbers to tell you what we can play with it.
Okay.
Yeah. So, Yeah, sorry, I don't have concrete, I don't remember concrete. We looked into this, but I don't remember the concrete numbers.
Okay.
These are good questions. Okay, so part 2. So this was all in the imperative procedural world. Okay, so now I said in the beginning, function programming is parallel safe. That's a wonderful thing. That means you don't have to worry about races or anything like that, okay? But the challenge there is that, well, you just don't have high performance, okay? You don't have to worry about races, but you don't get high performance. So the key problem there is memory management, memory management, memory management. So simple function programs just allocate so much data. It's just, you have to solve this problem if you want to get high performance. And if you can, right, you are talking business. Right? You've got a functional program that actually runs fast. That's the dream. That's what we want to do. So, we've been working on this project and extending the standard ML language with fork-join parallelism. Actually, there are other forms of parallelism like futures and etc., but I'll focus on fork-join here. This required extensive modifications to the compiler. We've been doing this for the past several years now. Now, the key feature that we've been focusing, because memory is so important, is memory management, memory management, memory management. Specifically, we've been focusing on the locality problem, right? So as much as the fact that the language actually does not allow the user to manage memory explicitly is a problem because the user cannot optimize. But it's also an opportunity because the language, the system, can manage the memory in a much better way than the user can, especially in a parallel computation model. Okay? Because in parallelism, memory management, try it with C++, it's just incredibly difficult. It's exponentially difficult than regular management. Now, this language actually says the user does not see that abstraction. He cannot see what's going on in the memory. So there's an opportunity to manage memory properly. And this is what we've been focusing on. So I'm just going to give, there's a lot of detail here ordinarily. But I'm not going to get into that detail. Specifically, I'm not going to talk about the semantics. And I'm not going to talk about the implementation, which the semantics has been complete with accompanying Coq proofs. The implementation has been complete, according to my student, for the past couple of months until he finds the next bug. But so we're chugging along there. So I won't talk about those, but I'm going to give you a overview of the conceptual ideas here, which I think is I'm very excited about this particular project here. So let's see if I can communicate to you what's interesting here. So good locality is essential, right? So in merge sort, we measured a 10x difference between a program that has good locality and poor locality. But how do you optimize for locality? Well, you really can't. The reason is that there are so many different levels of caches on your machine. There's NUMA. The memory system varies from one machine to another. It's always changing. Okay, so that's the hardware complexity. At the software level, if you want to do this, you have to commit to programming at a very, very low level of abstraction, control memory allocation. That's not sufficient because the point of locality in a parallel computation requires, like if you want to get good locality in a parallel computation, you have to co-locate data and computation in the same node. Okay, so that means control over scheduling. Now that is extremely difficult because schedulers are often non-deterministic. Right? They have to make decisions based on who is busy, who's doing what at the same time, at what time. It's very hard to do that, but you might be able to. But anyway, bottom line, it's difficult to do. It's messy. So our conjecture is that it's possible to do this in the runtime system. And let me show you how. So let's again go to our nested parallel fork-join program. It's represented as a DAG like this. It's a DAG of threads. And the scheduler, what it does is it does simply the threads correspond to these pieces of code, all this good stuff that you know now. So now what the scheduler does is that it maps this DAG to process source. For example, it might map the first node into P1, and then second node on the right here onto P2, and this P3 and P4, and so on. So this is what you get as part of the scheduling. Now, as this scheduling takes place, threads are migrated between different processors, and therefore the data needs to be brought to different nodes than they used to be located at. So this naturally disrupts locality. Okay? So this is the one challenge that somehow we have to solve. The other challenge is that in a garbage collected language like ML, every once in a while garbage collection kicks in and clears up all the caches because, well, the processors execute the garbage collection algorithm, so all of the caches are flushed effectively. So you experience thrashing. So we have to solve this problem as well. So the idea, the overall idea here is, in the runtime system, to couple these guys, the program, the mutator, so to say, in the garbage collection lingo, the scheduler and the memory manager, in such a way that they work basically to optimize locality and somehow map all of that to the hardware so that the locality in hardware is mapped, the locality in software is mapped to locality in hardware. Okay? But the question is, how do you do that? So a couple of observations. So the first observation is that if you look at concurrent threads like this, right, so these are some concurrent threads, that means these threads are not, there is no path between them. There are no dependencies between them. They can all be executed in parallel. A key point here is that in any data race program, that's not true, but in a functional program, and in many data race programs, these threads do not read from each other. If I draw the reads as these arrows, you cannot have arrows like that in a functional program where those pieces are concurrent. You just don't have them, period. So that means that all the reads go actually up to the ancestors, okay, up the path in the DAG. So then what I can do is I can allocate one heap per thread, like these are these little square boxes, and effectively allocate the working set for each thread in the heap that's local to that thread. Now here's what the cool thing shows up. Now recall that these guys do not read from each other. That means I can garbage collect them concurrently. I can garbage collect this as that guy is executing. I can garbage collect these two as that guy is executing, and so on. My garbage collector does not have to rediscover the structure of the computation, which is already given to me by traversing the memory graph. The computation tells me where the independencies are, so I take advantage of them rather than rediscovering what's independent in the memory graph. Okay? Furthermore, right, I can interleave the GC and the computation in any way that I like. These pieces can be collected in any essentially order, right? So that can collect, it can run, it can collect, etc. They're all independent. Second observation. Now, let's look at the heaps that are descendants of the same thread migration. For example, we had a migration at P2 here, at P1 there, P3. So let's color those heaps. We get these paths. Well, because that's sort of how, that's an invariant of the model here. And let's put them all into the same heap instead of thinking of them as separate heaps. That's a natural thing to do because they are mapped onto the same processor. So the mini heaps that are going to now go to the same heap are drawn in the same color. But what we get is a heap hierarchy that effectively matches the sponsing tree of the computation. Okay, so we get a tree of heaps instead of a DAG of heaps. So memory is now tree structured. What's beautiful about this is that, well, the hardware is tree structured. So the hierarchy, memory hierarchy is tree structured. So now you can map this thing onto that thing. Okay? And basically, the point is that the structure of the computation and the structure of the hardware are essentially the same. That's not an accident because over the 100 years, that's exactly what we've been doing. But we didn't know how to take advantage of parallelism. Now we do. Okay? Good. So, summary, what we do is basically, we observe scheduler decisions, and for each migrated thread, we create a processor mapped heap, and garbage collect heaps concurrently, and map the heaps, the heap hierarchy, to the hardware hierarchy to maximize locality. Okay. Do I have how much? Yeah.
Quick question.
Yeah.
Seems to be a trade-off with the greedy scheduling property. So if the descendant of that red P4 at P3, or well, I guess there are many red P4s, but yeah, well, let's
Sorry
say
about
that
that.
one, the P2 below.
Well, it can happen, of course.
Yeah,
Yeah.
it's important for anyone, the parent and the child to be scheduled on the same core, right?
Correct. Yeah. Correct.
So, but it may be that another worker is ready to execute the child, but you want to wait so then that core is available. So do you constrain the scheduler, and that goes against the greedy scheduling property?
That's a beautiful question. So the question is, well, the Worktime Principle that I mentioned in the beginning assumes that you've got a greedy scheduling principle, which means that if there's an idle processor, you feed it as soon as possible, right? So if you want to maximize locality, right, so if you want to, for example, map this to P3 as well, because there's locality, natural locality here, you might say, I'm not going to send this to P4. So I think that opens up a whole new research direction, basically. How do you design scheduling algorithms where, yeah, we have not started looking into that, yeah. Questions? Yeah.
Your allocation strategy, when you get out of memory, it will be on the smallest cache. So whereas in a functional language, it's a whole memory that, and how the programmer is going to control that, he doesn't know anything.
The programmer doesn't know anything, no.
So it will be cut at the smallest cache that you have, or you will reallocate memory elsewhere?
Oh, so you reallocate memory immediately. So the implementation, what it does is that there's a goal. You can grab a page and then you bring it, but you grab a whole page. So, yeah. Okay, very good. So just very quickly, let me tell you about how we use this in parallelism. So Carnegie Mellon has been very generous. So what we wanted to do is we wanted to inject. This actually happened before I arrived at Carnegie Mellon. So Guy Blalock and Bob Harper had the idea of injecting parallelism to the curriculum such that parallelism was basically taught from the beginning. So Vivek showed this picture of a parallel programmer today. He first writes the sequential code, the for loop that I showed in the beginning, right? And then he goes, oh, how can I make this parallel? Oh, why don't I replace this for with a parallel for? And then he gets into a data race and etc. So what the vision here is that, well, we don't want to start with serial code. We want to start with the parallel code first. Okay? And if there isn't parallelism available, then you can think about the serial code. So we want the students to learn about parallelism from the start. Okay? But for those of you who have a deeper understanding of parallelism, parallelism is just such a general term. There are many different forms of parallelism. Which form of parallelism are we going to teach if we want to include it in the curriculum in such a way that it's very fundamental, right? So what we decided to do is to actually simply focus on this work and span model and do not worry exactly about how parallelism is implemented. What's important is that students understand the work and span model so that they can design algorithms with low span, which means a lot of parallelism, but not worry too much about how exactly the implementation is done. So there is a bit of an abstraction there. And in order to achieve that, we chose to follow a functional style with no side effects, at least from the perspective of the student. In the implementation, there could be side effects, of course, so that they don't have to worry about data races. So they don't spend their lives, right, debugging data races in the context of a class. So we've been developing a book based on these ideas and developed this course. The course is a whole array of assignments, 12 assignments. Now, what's interesting is that even though I told you that we don't want the students to worry about exactly how things are implemented, all the assignments are actually written. They all have written components, implementation components, written in PML and Passel, C++ and Passel. Okay, so now you can ask, are we completely nuts, right? How can you teach parallelism to undergraduates? So by the way, these are sophomores, second-year students, and we teach about 400 of them each year, so 200 in the fall, 200 in the spring, so a lot of them are going through this pipeline now. So how do we actually expect to teach parallelism, what appears to be a very hard topic to undergraduates, and so many of them are we completely crazy is the question here, right? So, well, we really are not, because many algorithms are actually naturally parallel. We've been sequentializing them because our hardware has been so, right? It's an artifact. It's not a mathematical reality. It's just an artifact of the hardware. So it turns out it's actually, you just start with a different set of tools and you can teach parallel algorithms to your students. It's not too difficult to integrate parallelism into a traditional algorithms course. Okay, so there are a few issues here. What model, again, and not all parallel problems admit parallel solutions. And when these arise, we deal with them, right? For example, if you're going to do an ordered DFS, you don't really have a good parallel solution. It's a p-complete problem. So you talk about that, and you talk about the sequential algorithm. Right, so why functional programming? So far I focused on the safety reason, but there's another important reason. It's extremely powerful, right? It supports higher order functions, which has been becoming more and more important, both programming and algorithms. And as a side effect of that, it encourages use of collections and aggregates, which also simplifies programming a lot by raising the level of abstraction. Now, a potential pitfall here is that array updates are not constant time. So we kind of deal with that by having an basically imperative implementation under the hood, but still offering a functional interface. But there is some opportunity for real research there. Another issue is that, well, by using functional programming, we basically narrow our audience to those people who are familiar. Now, one more thing I want to mention is that the book and the material is written without assuming a specific language. So this we've decided to pursue pretty rigorously after experiencing seeing that language dependence actually creates issues. What do I mean by language independence is that we have actually a pseudocode language that's reasonably formal that we call Spark, and the book uniformly uses this language. The language is mathematical, it's functional, it translates very naturally to ML, but also C++, though with some effort because of the memory allocation problem. Right, so the students basically code, 80% of their coding is in ML, and in the last 3 weeks, we switched to C++, and they get to run their code and see how it works, and see that all they've learned actually translates to C++ and to a language that can be run in parallel today. So a very brief overview of the lessons learned. I think it would be fair to say now that now we know it's possible to cover both sequential and parallel algorithms together from the beginning, from the start. Students do well. It's not any different than usual. They still complain, right? One interesting thing is that the course is challenging for even our top 1% of the students, which actually they constantly complain about. This top 1% actually constantly complains about the fact that the courses are not challenging enough. Because we have some students that come in with a lot of training, but all of their training is in the serial domain. So they hit the wall. And that's a great thing, so we're very proud of that. Now, on the other hand, 75% of our master's students drop or fail, literally, which are not undergraduates, but our master's students drop and fail because they don't know functional programming, okay? This is after paying, so they actually...
75% of all of those who take the course.
Or who take the course, yeah. So that's a good, this percentage might increase if they generalize. So those who try, they come and they're very excited, we want to learn about parallelism, blah, 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 blah. They start, and then about 2 weeks later, all right. So we're working on this. Obviously, this is not a good problem, right? It used to be some percent. It used to be 100%. It used to be 100%. So we're getting better at this. So language independence is important because so far we've been able to translate the whole thing to PML, and C++ we've also translated partially to C++, about 30% at this point. And researchers in Italy are creating a Scala version of this, so if you're interested, you can do it in whatever language that you like, and contact us if you would like to teach. Thank you.
Is it related to the fact that ML is strict, that is with Haskell, monads, and so on, this would be the same or different?
Oh, good. What's the question again? So what is related to the fact that ML is strict?
It's all the implementation that you
Oh, yes,
showed.
yes, yes, yes. Strictness is essential because without that, we don't have a cost model. I mean, we don't know how to do the cost model in a clean way. Obviously, there's a lot of work in the Haskell world. In some ways, cost semantics have been really utilized in that world because of the difficulty of predicting cost of Haskell programs, but we don't know how to do it in a clean, simple way.
Case for strictness.
Yeah, strictness. In fact, SPARC stands for strict parallel.
Do you also teach correctness proofs for these algorithms?
We do, but they're very simple. Sorry about that. They're very simple. They're because they're purely functional. You know, parallelism doesn't add any complexity. It's there as complex as they would be in the serial setting. That's a very good point. That's a strength, right?
So you had these nice performance graphs for the C++ version, and what about the managed heaps or the whole heap?
Oh yeah, so that's we are working on them. They're not ready. Yeah, yeah, we are working on them as I speak, but they're not ready.
For the C++ variant, you had this cost function there. But for the ML one, you didn't. Is that automatically inferred, or what's the story?
No, actually, we don't even have that in ML right now. So in ML, what we are trying to get to work right now is just fork join vanilla. The hope is that the abstractions that we discover in the C++ world, hopefully will make their way into the ML world. But ML is coming behind. Things are a lot harder in the ML world.
Thanks.
A paradigm with functional programming is lists, and so I don't see how the parallelism is going well with this list programming.
There are no lists.
You have only arrays.
Sequences. So not only arrays, but so basically the way we teach is that we have a mathematical sequence notation in the pseudocode language, and then we specifically say, okay, so this is how you write your program. And based on the operations that you need, you can use a list implementation, you can use an array implementation, you can use a tree implementation. So, and we have separate cost specification for each. Yeah.
So just a quick question. There was this nice work by Chris Okazaki.
Yeah.
The purely functional data structures. Do the students write those? Try to parallelize them? Or?
Well, so a very interesting. So a lot of that work actually is lazy, based on laziness, and laziness is imperative. That's a big problem because imperative programs don't work very well functionally.
So here you capture things like prefix sums, this kind of things.
Oh, so we have a lot of prefix sums, a lot of reduces, scans, prefix. Yeah.
I guess you can capture most of the streaming computation, like map reduce, also in this.
That's trivial, obviously. Yeah.
Right.
Yep.
Why do you say that laziness is imperative? I thought it's sort of removing the imperativeness out of strict programming.
It's implemented using imperativeness under the hood because any lazy computation is basically represented as a reference that points to a thunk. And when that thunk is evaluated, that thunk is replaced by a value. So that operation basically is an imperative update. And in a functional program, you could have many threads actually trying to read that at the same time. So, yeah. Okay. Yep, that's the challenge in the lazy program. Yep. Thank you. Okay. Thank you all.